Okay, now we're back again. I'm gonna proceed this SPC lecture. Yeah. Okay. This is on choice of control limit. We all know that there are two important aspects in designing control chart. First is related to sampling, and the other is choice of control limit. Yeah. So this is the one, choice of control limit. So here it means that the choice of alpha. Or we know it as a significant levels, yeah, or level of significance. Normally, we choose alpha from the range of 0.01, 0.05 to 0.10. Normally, we use 0.05, yeah, right. To decide which value for us to use for our control chart design, we also need to understand beta, yeah. So what is beta? Beta is type 2 error. So alpha and beta are the errors that we have made. And these mistakes or error has been made on the decision that we make for our hypothesis testing. Yeah, remember under hypothesis testing, we have the null hypothesis and we have to decide whether or not we reject or not to reject the null hypothesis. Okay, so how do we do that? By comparing our computed test statistics and the test criteria. Okay, so the decision whether to accept or to reject null hypothesis depend on two things. Okay, number one, the sample that we use from our study. Yeah, so this sample will help us to compute our test statistics, isn't it? Yeah. So based on this test statistic, we're going to compare it with our test criteria. So in coming up with the test criteria, we have to decide on the level of significance, and that is alpha, isn't it? Yeah. So therefore, when we make decision, we are bound to make error. Yeah. In any decision at all, we are bound to make errors. Okay. So these wrong decision are called type 1 and type 2 error. Okay, basically what is type 1 error? Yeah, type 1 error is rejecting the null hypothesis and to accept the alternative hypothesis. Yeah, whereas in actual fact, the null hypothesis is true. Yeah, so this is the error. We are, based on our decision, we are rejecting the null hypothesis, but in actual fact, the null hypothesis is true. That's type 1 error. For type 2 error, it is failing or not to reject the null hypothesis, yeah. Whereas in actual fact, the null hypothesis is false, yeah. The null hypothesis is false. It is not true. But the mistake that we have made is we do not reject the null hypothesis. Yeah, we accept the null hypothesis. So basically, those are the two types of error. Now, coming back again, our decision is based on the sample that we gather from the population. Okay, so from this sample, we estimate some sample statistic that we use to compute test statistic. Yeah, I'm repeating this again. So, based on the decision, we will infer what we gather from the sample onto the population. Yeah, so there are two different sets of information here. One set of information is based on the one that we derive from our sample. Yeah, the sample statistic. Yeah, that we obtain from our sample. The other set of information is the actual information from the population. Okay, so in many cases, we would say that the population parameter is unknown. Yeah, so we have to rely on sample. Yeah, but the truth is out there. Yeah, the truth is in relation to the truth related to the population is always out there, whether we know it or we do not know. Yeah, In some cases we know, in some cases we do not know. Therefore, we have to rely on our sample statistic. Yeah. Okay, so there are two situations here. Number one, the decision that we make based on our sample. Here, for example, we base on our example. The result is not significant. Therefore, we do not reject the null hypothesis. The other decision is yes, our result is significant. Therefore, we reject the null hypothesis. The other situation is whereby the truth is about the truth out there. Yeah. So in both cases, truth is either the truth is either correct or it is not correct. Yeah. So when we relate these two, there are four different possible decisions that we can come up with. Yeah. Remember, our decision is based on sample. Yeah, but the truth is out there. Number one, the first possible decision is in the sample, yes, we reject the null hypothesis, and the actual information from the population is the same, that we should reject the null hypothesis. Yeah. Next one is from the sample, yes, we reject the null hypothesis, but from the population, the information, the actual information is that we should not reject the null hypothesis. So this is what you call false positive. Yeah, you have a false decision, whereby decision is actually a positive decision. Yeah. Thirdly, is whereby from the sample, no, we do not reject the null hypothesis, but the actual information from the population is that we should reject the null hypothesis. So this is what you call false negative. And finally, from the sample, we do not reject the null hypothesis. Yeah, and the actual fact is that we should not reject the null hypothesis. So in general, this is true, negative. Both are not correct. Okay. I also have a link here where you can also have a look, yeah, on what type 1 and type 2 error is. Okay. Now, in relation to a choice of control limit, yeah, in choice of control limit, for type 1 error, which is alpha, this is the situation whereby we reject the null hypothesis, whereas in actual fact, we should have not reject the null hypothesis. So in control chart, this is known as false alarm. Yeah, this is the situation whereby on the control chart, the point lie outside the control limit, but the process is actually in control. Yeah. So for false alarm, it simply indicates that although the points lies outside control limit, the process is actually in control. Yeah. So in this situation, this is a situation of false alarm. Yeah. The other two error is the second error is beta. Yeah, this is where you fail to reject null hypothesis when we should have reject the null hypothesis. Yeah. So this is similar to the problem of insensitivity of our control chart. Yeah, so this is also a problem. Yeah, this is another error which relate to a problem. Yeah, so this is the situation whereby the point does not actually lie beyond the control limit, whereas in actual fact, the process is out of control. Yeah, so the process is nevertheless out of control. It is actually out of control, but you don't see any point that should indicate the process is out of control. Yeah, so this is due to the problem of type 2 error. Okay, so type 2 error will lead to the problem of insensitivity of control chart, and type 1 error, which is alpha, will lead to the problem of false alarm. Okay. Now, again, under Shewhart control chart, the choice of control limit is actually fixed here, because we set a 3 sigma control limit, whereby the probability of type 1 error is 0.007. Yeah. So, for the probability limit, type 1 error will be chosen directly. For example, if we have alpha equals to 0.001, this will give you 3.09 sigma control limit. Yes, so this is how you compute the control limit. Yeah? And also you will see in Montgomery, yeah, it does suggest the other two limits. Yeah. Apart from upper and lower control limit, they also suggest the warning limits. Yeah, they have upper warning limits and also lower warning limits. Yeah, so the computation is very much the same. It's just that for the normal upper and lower control limit, it is computed as such mu plus minus 3. Yeah, the limit, yeah, or the constant is 3 sigma, yeah, or 3 standard deviation. But for warning limits, it is 2 sigma limits. Yeah, the computation of limit is based on 2 sigma. Yeah, the normal control limit, it is based on 3 sigma. Yeah, so in this case, this is to the 2 decimal places. Yeah, 3.09, but we normally take it as 3. Yeah, so that's why when we want to compute our upper and control limit, it is simply mu plus minus 3 sigma. Okay. So the choice now is whether you would like to have wide control limits or narrow control limits. Yeah. Remember, we have the problem of a false alarm and insensitivity of control chart. Yeah. So in general, if you have wider control limits, yeah, your control chart is insensitive, or it is not that sensitive, yeah, because it fails to detect some points which are actually out of control. Yeah. The other situation is whereby you have narrow control limits. Yeah. So in such situation, for narrow control limits, it can lead you to the problem of a false alarm. Yeah, false alarm here meaning to say that this point is not actually a problem to the process, but due to the choice of control limits, the control chart will show that this problem has result in a out of control process. Okay, so again, the choice of control limit will depend on alpha, and this value of alpha will determine whether your control limit is a wide control limit or it is a narrow control limit. Okay. So that is actually the trade-off between a wide or narrow control limit. It is simply to say that moving limits further from the center, it will decrease the risk of false alarm. However, it will increase the risk of insensitivity. Yeah. So this is when you move away or move further from the center line, you're going to come out with a wide control limits. Yeah. But in such a situation, there is a possibility of you are decreasing the false alarm, but at the same time you increase the problem of insensitivity of your control chart. Okay. Now, in the situation whereby your limits are closer to the center line, where you will end up with a narrow control limits, yeah, this situation will decrease the problem of insensitivity, but it will increase the risk of false alarm. Okay. Now, see if you can answer this question. Is it a small or large alpha that will give a wide control limits? Okay, give this a thought. Is it larger alpha or smaller alpha that will lead to a wider control limits? Okay, so larger meaning something which is close or rather 0.05 or 0.1. Smaller meaning like 0.01, yeah, as such. So you decide if you want to come up with a wide control chart. Are you going to have a small or large alpha? Yeah, that's the question, the first one. The second question is can you explain your answer in part 1 from a statistical point of view? Okay, so let's see if you can answer these two questions. Okay. Okay, right. Now we move on to patterns of control chart. Yeah, so in this diagram, we see some points. Yeah, in this control chart, we have UCL, upper control limit, and also the lower control limit. Yeah. So what can you see from this diagram is that the pattern is very non-random in appearance. Yeah, non-random in appearance. Why we say that? Because 19 out of 20 points plot below the center line, while only 6 above the center line. Yeah, it's not a rough or a fair number. Yeah, between the upper and the lower center line, the area above the center line to the area below the center line. Following the fourth point, you can see 5 points in a row which actually increase in magnitude. Yeah, so this is what you call a run up, yeah, of the points in the control chart. And there is also unusually long rundown beginning with 18 points. Yeah, so if you look at the sample number 18, you will see a series of downward points. Yeah, so this is what you call rundown, yeah, of the control chart. So this is actually the non-random patterns of control chart. This is an example of non-random control chart. Okay, so how would you know whether a control chart has a non-random pattern or not? So a very simple guidelines or decision rule have been made by this Western Electric Handbook 1956. This is a very the foundation, yeah, of control chart those days. Yeah. So there are sort of guidelines here where you can determine whether the control chart has a non-random pattern on. Yeah. So if it has a non-random pattern, 1 point will plot outside the 3 sigma control limits. Yeah, it goes beyond the control limit. 2 out of 3 consecutive points plot beyond the 2 sigma warning limits. Yeah, so in order to analyze whether control chart has a non-random pattern or not, yeah, you should also come up with the warning limits and see whether there's any 2 out of 3 points actually lies beyond the 2 warning limits. Yeah, so remember you have upper and lower control limit. You can also have a lower and upper warning limits. Yeah. Next, the guideline says 4 out of 5 consecutive points plot a distance of 1 sigma or beyond from the center line. Yeah, meaning to say that majority of the points actually close to the center line. Yeah, this is a situation of hugging the center line. Yeah. Last one would be 8 consecutive point plot on one side of the center. Yeah, so say for example, you have the middle line as a center line, and there's 8 consecutive points that actually plotted either on either side of the center line, either above or below. Yeah, 8 consecutive points, yeah, are plotted on one side of the center line, yeah, either above or below. Yeah, so that is the guideline given in order to detect whether there's a non-random pattern in a control chart. Okay. Now let's go to the control chart application. As you know, there are two phases of control chart. Yeah, phase 1 is what you call a retrospective analysis. This is the stage where the process data is used to construct the trial control limit. Yeah. So what does it mean? At the very basic level, control chart plots are actually based on the historical data set. Yeah? So when you have the original data set, that is what you call historical data set. So given this set of historical data set, you will plot the control chart, or you will come up with the control chart plot. Yeah? Either by using a manual, or you use it through a software. Okay, so normally if you have large number of observation, you would simply use software to plot the control chart. Yeah, so the objective at this stage is to identify any outliers and to discard them, rerun control chart iteratively until all points are within the control limit. So this means to say that if you have the historical data set, you're going to plot the control chart, yeah, by using, for example, by using software, and you identify there are some out of control points, yeah, or points that lies beyond the control chart, or beyond the control lower and upper control limit. Yeah, so normally if you were to plot control chart using software, yeah, the upper and lower control limit will be automatically computed by the software, and it is straight away shown on the control chart itself. Yeah, so from the control chart you will identify if there is any points which lies beyond the two limits, yeah, upper and lower control limit. And if you detect there's any point which show that the process is out of control, you will delete this point. Yeah, because in general at this stage, those points which lies beyond the control limit are actually called the outliers. Yeah, outliers are the point that shouldn't be there in your data set. So you're going to exclude this point. You're going to discard the outliers. Yeah. So once you run that, you're going to plot the control chart again, meaning you rerun using your software to come up with another control chart. Yeah. So from this second control chart, you will identify the control limit has changed. Yeah. If you to compare it with the earlier control chart, yeah, because you have a different set of data, yeah, therefore the computation will be slightly different because the mean and standard deviation value has changed. Yeah, so the process is said to be iteratively, because if in any stage once you come up with the control chart, you see any out of control point, you will delete and you're going to rerun. You rerun, you're going to see a new control limit, check whether there is any points lies beyond the two limits. If there are, then you're going to discard it again and again until the stage where you come up with a control chart where the points are all within the control limit. Okay, so this process is iterative. Yeah, you're gonna do it again and again until you find until you have deleted all the out of control points or the outliers. Yeah, so when all the points are within the control limits, the process is said to be stable and statistically in control. Yeah, so this is what we normally say. When all points are within control limit, the points are believed to be in control. Yeah. So when the process is in control, it is a stable process. So the word here is statistical in control. Therefore, it is a stable process. And that is only happen when all points are within the control limit. Okay, so please take note that at this stage, or rather at phase 1, the retrospective stage, this is the stage where you are trying to come up with a process which is believed to be in control. So there be a lots of outlier deletion during this phase. Yeah. So this is the phase where you will ensure you will rerun control charts until all points are within the control limit. Yeah. So why are you doing that? Because this is the stage where you're going to estimate the mean and standard deviation. Okay, so the estimated mean and standard deviation will be applied for phase 2, where the actual monitoring process takes place. Yeah. So phase 1 is the stage of parameter estimation only. Yeah, you are not assessing the performance of the process. Yeah, you only would like to discard all the outliers, and you would like to ensure at the end of phase 1, you will produce a process which is believed to be in statistical control. Why? Because all points are within the two limits. Yeah, and in that situation, you are actually having the sample that you have in hand, where the points are all within control limit, is called reference sample. Yeah, so originally you have the historical data set, the original sample, but when you have deleted all the outliers, this is what you call sample reference. Yeah, this is what you call sample reference, and from sample reference you will estimate the mean and standard deviation. Yeah, so this estimated mean and standard deviation will be applied during second phase, phase 2. Yeah. So in phase 2, this is called prospective analysis. Yeah. So this is where the actual monitoring process takes place. Yeah. So so if you were to do process monitoring, you would first assume the process to be reasonably stable. Yeah. But to ensure whether it is stable or not, you are going to apply the mean and standard deviation that you have estimated from phase 1. Yeah? So meaning to say that for phase 2, it is a totally different set of data set. Yeah? So during phase 2, you're going to have a new data set whereby you would like to monitor the performance, yeah, of the process. Yeah. So in phase 2, the emphasis is on process monitoring and not to bring an unruly process into control. This means to say that during phase 2, there will be no outlier deletion. Yeah? If you see any outliers or any points which lies above the two limit, it simply means that the process that you are monitoring is not in control, or it is not in statistical control. Yeah. So this phase 2, you are only monitoring the process. Yeah. You are not doing any, you are not deleting any points at all. Yeah. You only observe if there's any point lies beyond the two limits. It simply means that the process is not in statistical control. And also you can say that the process is not stable. Yeah, although originally you assume, yeah, it is reasonably stable, but after process monitoring you can decide whether or not the process is actually stable or not. Yeah. So control charts are effective at detecting large sustained shift in process parameter. Yeah, it can also detect if there's any measurement errors, any data entry errors, yeah, and others, which are the assignable causes. So meaning to say that if there's any problem of shift in the process mean, and these shifts are a large mean shift. Yeah, we talk about size of mean shift earlier on, yeah, in the earlier part of the lecture. Or rather there's any problem in data entry, those will relate to some points to be located beyond the two limits, yeah. And if that's happened, that is the situation whereby the process is not in statistical control, yeah. So those problems which cause process to be out of control are called the assignable causes, yeah. So these are the assignable cause of variation, yeah. So we have actually looked at this type of source of variation, yeah. Assignable cause of variation. In some terms or some texts, yeah, it is called special cause of variation. Okay. Now, next part is process capability. Yeah? Capability versus control. If you are looking at control chart as a process monitoring tool, this is actually you are actually looking at the you are actually controlling, yeah, the process. Yeah, it is actually a process for a tool for process control. Yeah, control chart is a process control tool. But at the same time, it is also good if you can study the process capability. Yeah? So process capability will compare the output of a process to the specification limits. Yeah? So if you remember specification limits, we have lower and upper specification limits. Yeah? So normally upper and lower specification limits are actually the limit or the specification being given by the design department. Yeah, so if you were to produce items or product, it should be produced the measurement, yeah, of the dimensional measurement of your product shouldn't exceed the upper specification limit, and also it shouldn't go less than the value shouldn't be less than the lower specification limit. Yeah. So these two values are actually values from the specification limit. Okay. So you can actually compute the process capability by computing the capability ratio. Yeah. So it is actually the ratio of the spread between the process specification. Yeah. So it is called the specification width to the spread of the process value. So there are two different things here. Yeah. Number one is the values given by the specification limits. Okay. The other one is the dispersion. Yeah, the actual dispersion of the process data. Yeah. So what you have, the data in hand, will give you the distribution of process data, the actual data. So from this actual data, you can compute the standard deviation. So as you know, standard deviation measure the dispersion of the process. Okay, so the specification width is based on the upper and lower specification limit given by the design department. Yeah, but if you were to measure the actual process data, that will give you the process standard deviation. Yeah, so in order to compute process capability, you need to have these two values, lower and upper specification limit, and also you have to know what is the process standard deviation. Yeah, so you can simply do that by computing the standard deviation from the dataset, from the process dataset. Yeah, so the formula is simply the difference between upper and lower standard deviation divided by 6 sigma, or 6 times the standard deviation. Yeah, so 6 here is actually related to the concept of 6 sigma. Yeah, okay, so standard deviation here is actually the value come from process data. So by computing these capability indices, yeah, you will know whether your process is capable or not. Is your process capable of producing items which should not go above the upper specification limit, or it shouldn't go lower than the a lower specification limit. Okay, so if you were to do that, you can compute the capability indices. Yeah, in general, capability indices should be equals to 1. Yeah, if it exceeds 1, it means that the process data actually goes beyond. Yeah, it goes beyond the lower and upper specification limit. Yeah, so a good capability indices is the value which is close to 1 but not exceed 1 in general. Yeah, we're going to look into capability indices when we use JMP software later on. Yeah, there'll be a computation for capability indices from the software itself. Okay. So again, process capability calculation will make little sense if the process is not in statistical control because the data are confounded by special causes that do not represent the inherent capability of the process. Yeah? So this simply means to say that if you were to measure the process capability, you must first of all ensure that the process is in control. Yeah, so you must do your best so that the process is in control, is in statistical control. Then only you can compute the process capability. Yeah, only by doing so the value of process capability is more reliable. Yeah, or else it is not, because the process there are still presence of special causes or presence of assignable causes, yeah, which makes it not stable. Yeah, so remember, if you want to produce or you want to compute process capability, at least you have to ensure the process is in statistical control. Okay, so there are two important criteria in assessing or in measuring the performance of a process. Yeah, number one is based on its control. You must ensure that the process is in control, and the other one is based on its capability. Yeah, so you must also ensure the process is capable. Yeah, capable meaning it will produce items which is within the upper and lower specification limit. Okay, in control meaning the process the process data is within the upper and lower control limit. So the ideal situation is whereby the process is in control and at the same time it is capable. Okay, as shown by this diagram. So lastly, we're going to look at the statistical process control. There are 7 major SPC. Yeah, number one is check sheet. Yeah, see, this is check sheet is normally the document that you will find at the shop floor or at the factory itself. Yeah. Next is Pareto chart. Yeah, Pareto chart will actually tells you in general. Yeah, Pareto chart is used to identify problems. Yeah, so you will collect all the relevant data and you're gonna come up with chart. Yeah, so this is something similar to bar chart. Yeah, so it is plotted as such for that particular items or the particular attributes or variable which has highest frequency of defective or problem will be shown by this Pareto chart. Yeah. So in this example, it show you the tank defect data. Yeah. So this is different types of data. Yeah. Defect data on defect for a tank. Yeah. So it shows here that incorrect dimension is has the highest frequency. Yeah, meaning the major problem of defect for tank is actually incorrect dimension. So Pareto chart will give a quick information on what are the areas that you can give more attention to further improve the process, and towards the end of the day you will produce the quality of items or product being produced. Yeah. So this is another other example of Pareto charts. Yeah. This one is cause and effect diagram. Some texts will call it fish and bone diagram, or even Ishikawa diagram. Yeah. So again, instead of presenting the problem area in Pareto chart, you can also use cause and effect diagram. Yeah, for cause and effect diagram, you will have the information on what will be the attributes or what will be the area that will cause those problems. Yeah, so in general, for fish and bone diagram, you're going to have these 4Ms. Yeah, we call it 4Ms in production, which will give you details. Yeah, the details on the possible defects. Yeah, the possible causes of the defects that you have in your product. Yeah, so the 4Ms are actually machines, material, methods, measurement, and personnel. Yeah, so for example, if you talk about machine, some of the attributes of the machine that you can look into are, for example, wand tool, too much play, surface finish, paint and spray speed, a wrong tool, ambient temperature, dust, paint flow rate. Yeah, so this is example which is related to machine. Yeah, for material, methods, so on and so forth, they have their respective attributes or area that people can look into in order to identify where does the problem comes from. Okay, the causes of the quality problem. So this simply will show you how you can construct a cause and effect diagram. Yeah. But you first of all, you must know the details of the production, and then only you can come up with cause and effect diagram. Yeah, so the very basic one is to come up with this 5M and go into greater detail for each and every aspect of your production. Yeah. Okay, this is defect concentration diagram. Next is scatter diagram. Scatter diagram, you're quite familiar. This is like scatter plot. Yeah, you know how to come up with a scatter diagram or scatter plot. Yeah. This is an example of how SPC implementation has been done under the quality improvement program. So you have phase 1 and phase 2. Yeah. So you can have a look here what is actually can be done under phase 1 and exactly how you come up with the control chart under phase 2. Okay. These are the example of Pareto chart. Yeah, so this is a real example. Yeah, whereby they are detecting the average rate of rejects for each and every production line. Yeah? So CFD, JD, HG, these are all the names of production line. Yeah? So the average rate of reject, yeah, has been recorded, and it shows that production run C has the biggest problem. Yeah, these data are for January, February, and March for the year 2007. So it's been decided that more work should be done to improve the production shift at line C. Yeah. So this is the respective cause and effect diagram, yeah, for this case study. Yeah. And this is the control chart. Yeah, that the control chart on the reject rates of 6 production lines for January, February, March, and 2007. So this is actually come from this data set. Yeah, from this data set, they come up with this control chart, and it obviously show that the process is not in statistical control. Okay. And this is the Pareto chart, exactly which particular product which has problem. Yeah, and they need to give more emphasis on, yeah, to improve the quality of process. So okay, right? So those are the example. So we come to the end of the this lecture note on lecture video on SPC. Yeah? So thank you. Bye now.